To fit a linear regression between two continuous variables, we'll first start with the distribution of each of the individual variables, 2011 and 2012. We'll put them on the same axis setting so that we can more closely compare them. So we can see that the 2011 variables are slightly more tightly spread. So their mean is 49, their standard deviation is just about 11. We can see for the 2012 that their mean is 47 and their standard deviation is just slightly larger at 11.2. The range for 2011 and 2012 is relatively similar, though you can see that the lower end of 2011 is a little bit higher than the lower end of 2012. So 27.3 compared to 16.7. We can also see that as these values increase here in 2011, we're also seeing some similar increases in terms of the distances between the quantiles and even comparing the quantiles between the 2 years. Let's take a quick look at the normal quantile plot for both variables, though we already know these are normally distributed. Both years appear to be normally distributed. We'll be concerned with bivariate normality when we fit a linear regression, and in fact we'll actually be considering the normality of the residuals from our regression line. So let's go ahead and fit our y by x. Very similar, actually identical to how we did correlation to start with. 2011 is x, 2012 is y. Press OK. We'll go ahead and change the size and scale of this to be a little bit bigger so we have a little better of a view. And then we'll change the scaling of the axes to match. And so now we have a less biased view of what the line fit would look like. If it was a perfect fit, it would come straight up through these diagonals. So a 1-to-1 fit would give us a straight line or an R of 1. But what about a line? So under the red drop-down arrow, we're going to first fit our mean. This will put a line right across here that is associated with the 2012 mean. That is, if we had no information, no additional information, and somebody asked what the 2012 percentage antibiotic resistant MRSA infections was, we would give them this number. This would be the line. It would be at 48.4. That's the average 2012 mean antibiotic resistant rate. That would be our best guess without a predictor or without a useful predictor. So our slope here on this line is 0. That means that for every 1 unit increase in x, we would see no change or 0 change in y. That is what a slope of 0 is. What we want to know is actually the slope that fits this data. Is it different from 0? And that will be a t-test. We will be comparing our slope to a value of 0 using a t-test, very similar to the single mean comparison. So to ask for the fit line, can do that here from jump, and I'm going to change this line color to be a blue line here, and I'm going to change our mean fit line color to be a black line. Here's the black horizontal line is our mean, and the blue angled line here is our linear fit. There are multiple options under linear fit. We can ask for, in addition to changing the line of the color, we have our confidence bands around the line of fit. We can save our predicted values and our residual values. We could change our alpha level, and we could actually remove the fit line if we needed to. Some things that we'll want to look at. First of all, here is our equation for our linear fit. We can inspect our intercept here of 20.27. That means that if we extend this line right down to, that means if we extend this line all the way down to where it crosses, will cross somewhere at the 20.27 line. So what that means is that if 2011 is 0, then our 2012 prediction would be 20.27. It's also giving us our R-squared value, which we know is the amount of variability in 2012 that 2011 explains. We can also see, if we look further down, what our parameter estimate is. And our parameter estimate for 2011 is statistically significant, which would tell us that the parameter estimate of 0.58 is different from 0. That's what this test tells us. We could look at our analysis of variance table, which gives us our sum of squares total, our sum of squares regression, our sum of squares model, and our sum of squares error. Remember, this R-squared value here is simply this value, our sum of squares model, divided by our sum of squares total. It is telling us how much of this, what percentage of this, is accounted for by our 2011 value. In terms of this particular analysis, 2011 and 2012, we would say that it is a statistically significant predictor, 2011 for 2012. We could then give the line of prediction. We would say that for every 1 unit increase in 2011, 2012 would increase by 0.58. If it was a 1-to-1 increase, we would see that for every 1 unit increase in 2011, we would see a slope of 1 for 2012. You could also see greater than 1 values. This is the interpretation of this output. The one thing that we have not done is assess this model for the assumptions. These are supposed to be bivariately normal. You could ask for the density ellipse. That will give you sort of a way to assess this with your eyes. But with our linear fit, we can actually ask for our residuals. We can save them. We can also plot them. So let's plot them. We get 5 plots for our residuals. The 2 plots to pay attention to are the first one. We'll make this just a little bit bigger. And what you really want to pay attention to is that as you go across this way, as you go across the x-axis, that you see a random scatter of points above and below the line for each level of x. In addition, for the homogeneity of variance assumption, you want to see equal spread above and below the x. So because we have somewhat of a smaller sample size, you will see some holes. You won't have it perfectly filled in. But what you're really looking to not see are patterns. So a fan pattern would have the residuals do that. You don't want to see a curve pattern. What you really want to see is somewhat of a rectangular or oval pattern with equal spread and random plots. We can also see from the histogram here that this is somewhat unimodally distributed. That is, it looks a little bit like a Bell histogram. And we can go down here and look at the actual normal quantile plot. And again, the assumption here for normality is that the points will be along the line and within the confidence bounds. So it's the same interpretation of the normal quantile plot we've seen before. And we would like our residuals to be normally distributed. That is our assumption. They are normally distributed. We're looking for big departures from normality. You could also, if you wanted to, go up to the linear fit and ask to save the residuals. And you'll notice that there is a new column now in our data set. It has saved the residuals associated with each of our rows. So for 2012, we can see that it's predicting it to be 7 points off. You can actually save the predicteds as well. So we could see here for Delaware that while we observed a 36.8 in 2012, the model is predicting it to be a 44.1. And we'll do that for every row. I can actually do a plot of my residuals, just like I do any continuous variable. and I could ask for the normal quantile plot here, and it will give me the same normal quantile plot as we had in the output here for the model. So you can see that these plots are actually identical. So normality seems to be warranted, linearity seems to be warranted, our homogeneous variance seems to be warranted. Therefore, we could go ahead and interpret the result of this model. Our conclusion for this model will be that 2011 does a better job predicting the 2012 scores in comparison to simply the 2012 mean by itself. I'll remove the bivariate fit. You can then add in the fit on the confidence bounds, and you could then see how much confidence we have about our line fit. So while we're predicting this value here on this line, it could be as low as this or as high as this. And the confidence bounds have the same interpretation as the mean confidence bounds had. Again, we'd be predicting a value on the line here, but it could be as high as this or as low as that. So getting a mean prediction and a linear fit prediction is relatively straightforward from jump. What it is doing is comparing this mean value to this line fit. If they are statistically significantly different, then the mean line will cross right through the confidence bounds. If they are not statistically significantly different, then the confidence bounds will include the mean, and you can of course reference your p-value here, as well as making sure to interpret what your estimate means. Up next, we'll look at what to do if normality or linearity are not warranted.